Hello, everyone. So in this class, we're going to finish the part of fluid mechanics that is considered macro. That means that after that, we will be discussing microfluid mechanics. So far, what we've done is understand energy and momentum balances and mass balances, of course, um, from one point to another of a fluid system. We've added friction to the system. We've added work as a pump or a turbine. And we've seen the relationships between pressure, potential energy, um, velocity or kinetic energy, and then those concepts of frictions. And now we are going to use all that to different chemical engineering systems. And so in this class, we're going to talk about two specific systems, pack beds and filtration, which are two of the unit operations that are typically used in chemical engineering throughout different industries. So let's start with pack beds. A pack bed is essentially a column, typically a round column or a tube that has been packed with particles. Things that you probably have seen as a packed bed includes a carbon filter for water, like the carbon filters that you buy for your own house. Um, it could be a catalyst bed in which you have, say, a gas flow through a catalyst bed. It can be an ion exchange. It can also be oil or water seeping through soil or porous rock. So this is very relevant to things related to oil recovery, for example. In the lab, we use a lot of chromatography columns to separate chemicals, proteins, etc. And those are also based on a packed bed. In the packed bed, and separation typically occurs through different interactions, either chemical interactions with the particles, or as it's shown here in the figure, by size, where there are bigger particles that need to take longer to move through the system versus smaller particles can find a shorter path, and therefore you create some sort of separation. When you're considering this type of packed beds, the first thing that we need to do is do a few definitions. Consider that the fluid is moving through pores. So now we're going to have to define the volume of those pores, the porosity of the packed bed in order to develop a good fluid equation. So we have a cross-sectional area and a length delta. And so when we are trying to define an equivalent diameter of this pore, you're going to define it somewhere like this, where you say 4 times area over perimeter. And if I multiply that by length over length, then area times length gives me the volume of voids. And the perimeter times the length gives me the surface area, the wetted surface area, or basically the surface area in contact with the liquid or the gas. If we define this term A sub V as the surface area of a particle over the volume of the particle, then we can somewhat simplify this equation. You see that I put here area AV here. You have now a concept of epsilon, which is the void fraction. So let me put it here. Epsilon is called the void fraction. And so the void fraction times the volume is the volume of voids, which is what we had there. And then at the bottom, we're now defining that wetted surface area as the surface area, that AV surface area over volume, but then multiplying by volume and multiplying by 1 minus epsilon, which is essentially the non-void fraction or the area of the particle. What that allows us to do, as you see, is to cancel this volume. And now we have a definition that depends only on that specific surface area or AV and epsilon, the void fraction. Now, that's basically definitions for now. Now we're going to take that and use it in an energy balance. Now, remember that this packed bed, and this is first disclaimer, we're using a packed bed that is horizontal. And when that packed bed is horizontal, we will not have a delta C in our energy balance. We're going to, where the velocity on one side or another is the same. So U1 equals U2, if this is 1 and 2, and C1 equals C2, which means that at the end, what you have is a pressure drop related to a frictional loss. So you see that we have delta P over rho, the rho is on the other side, equals 2FF L over D UM squared. D in this case would be that equivalent diameter of inside the pores. And so we kind of use that definition that we just took to put here with a little bit of a disclaimer that this is the velocity, this UM here is the velocity inside the pore. So another way of putting that velocity inside the pore would be to take that velocity and divide it by the void fraction so that you get the velocity inside the pore through this definition, where the velocity U0 is the velocity before entering the packed bed. So this is U0, which is Q over A. And then when you divide by the void fraction, you are basically increasing that velocity as it increases inside here. So this would be UM inside of your packed bed. Okay. So by the definition of the volume of a sphere, you can rearrange that equation and use that diameter of the particle is 6 over the specific surface area AV for a sphere. So we're assuming that those particles are spheres for this calculation. And so now we cancel that AV and we only have the diameter of the particle, which is a lot easier to know, right? It's easier to put things in terms of the diameter of the particle because we typically know the particle that we are packing with. You can rearrange this equation, this energy balance, just to get an idea of the friction factor. So if I go and put it in this way, I have a value of 3FF equals to that delta P rho U0 squared dP over L, and then the epsilon cubed over 1 minus epsilon. That has been determined similar to the fanning diagram for packed beds. It has been determined that this value of 3FF is going to be equal to 150 over Reynolds plus 1.75. So that Reynolds, by the way, has a new definition. And so that's sort of important to know. We have this Reynolds as raw U0 diameter of the particle over mu 1 minus epsilon. Um, and so with that definition of Reynolds, you have these two terms that are here, and I'm pretty sure that if you remember the other equations, you will notice that this is a laminar term, and this is a turbulent term, which means that when Reynolds is very high, the friction factor is a straight line, similar to how in the fanning diagram, the friction factor did not change with respect to Reynolds at very high Reynolds number. So that's the 1.75. And then the laminar term, similar to the fanning diagram, is a number over Reynolds. Okay. Now, if we go back to that definition of the frictional dissipation being related to a pressure drop, and now we can put these together, 150 and 1.75 times these terms, which are basically these right here. And so what you have then is these two terms. Now, if we assume that this is a laminar flow through porous media, then this second term is not important. And therefore, you only have the first term. And that first term is what we use as Darcy's law. Darcy's law is a very important equation, especially developed for flow in soils, because in soils there's a very slow laminar flow, but it is applicable to many systems in which flow is laminar. So in here now we do a definition of permeability, kappa. So kappa will be permeability according to Darcy's law, and so that you have a very simple equation where the velocity equals minus the pressure drop permeability over viscosity and length. And you can find kappa just based on the properties of the system, basically the diameter of the particle and the void fraction of the packed bed. Now, important, obviously, is to have a disclaimer that this is for laminar flow only. And in the case of this new definition of Reynolds through packed beds, this is a Reynolds of less than 5. And I'll just rewrite here the equation for Reynolds number under the packed bed. Okay. So with these equations, the simple equation on Darcy's law, and then this longer equation, which is still applicable and can be used at any point, we typically have two types of problems or approaches to solve packed bed problems. And so I'll give you two examples of two problems and how they relate. Both of them, if I remember correctly, are include turbulent flow. So the laminar flow equation will not be used. But you will see that they are kind of rather simple to solve. One of them is when you are trying, we already have a system, and you're trying to calculate a certain new condition based on existing conditions. So this is an ion exchange resin, and you see that you have two conditions that you have tested. 10 gallons per hour gives you a pressure drop of 4 psi. 20 gallons per hour gives you a pressure drop of 10 psi. And with only those 2 points, you can now try to estimate the conditions of any other point. Specifically in this case, you're basically trying to find out what is the flow rate at 54 psi, which is the maximum pressure that the pump can deliver. So the way that you solve this problem is going back to this equation here of the two terms, and we're going to do a modification because you see that here we have velocity and velocity squared. And we're going to take that and convert it into flow rate so that we have an equation for flow rate. So velocity equals Q over A. So instead of velocity, I put Q over A. And instead of velocity square, I put Q square over A square. And now I have these equations, and you notice that these equations look very complex. I don't have in this problem the length of the column. I do not even have the properties of the fluid, even though we know it's water, we don't know the temperature, so it's kind of difficult to know what is the viscosity, etc. We don't have even the diameter of the particle. But there is something interesting about this, and it's that this term and this term are both constants. You see, if you do not change the particles or the packed bed itself or the fluid, these two terms are a constant. The viscosity of the water, the length of the packed bed, the void fraction, or the diameter of the particle are all constants. So basically you are left with an equation, and obviously assuming a constant temperature. The temperature is not changing, so that viscosity or density are not changing. Then you have an equation where minus delta P equals AQ plus BQ squared, where A is this constant and B is this constant. So if we have that equation, then we have an equation of two unknowns, and we have two conditions of Q and delta P. So with those, then you are going to solve this to find A and B, and then you have an equation to find any other condition. And in this case, we're going to use 54 psi. Now note that the units of this problem are a bit weird. They're gallons per hour and they're PSI, but it really doesn't matter because since A and B are constants, you can sort of include those conversions into these constants. So this is basically how you solve it. You say 4 psi equals 10 gallons per hour, and then 10 squared would be 100. And then at the second condition, 10 psi equals 20 gallons per hour, and 20 times 20 is 400. And so we take these two and we solve for A and B. The easiest is to multiply this by -2 so that you cancel the A's. You see that you have a minus 200B in the 400B, so 200B equals to 2. And so B equals 0.01. And then you solve with one of them for A, which equals 2.3. And now that you have A and B, now you have an equation where the pressure drop equals 0.3 Q plus 0.01 Q squared. Only true, by the way, when Q is in gallons per hour and the delta P is in PSI, right? Because those are the conversions are included. So now I can solve for any condition in this system. In this case, for maximum flow rate, maximum pressure of 54 psi. I put 54, 0.3, and 0.01, and this is a quadratic equation. So now I need to solve for that quadratic. Minus b plus or minus b squared minus ac over 2a. And that gives me that the maximum is 60 gallons per hour. So this is a simple system, but also a way for you to learn that whenever you're working with a packed bed, you can use this approach where if you're working, say, with a chromatography column, and that chromatography column works in a certain way, then you can run this chromatography column at a certain pressure and look at the flow rate, at another pressure and look at the flow rate, and then you develop your own equation for that chromatography column so you can predict what will be the flow rate at different pressures. Now, this is a bit of a more complex problem. Now we're talking about the different parameters within the packed bed. So you have a liquid that is pumped through a catalytic reactor that is shown here. There's spheres and consists of a horizontal cylinder. The spheres have a diameter of 2 millimeters. So this is our D sub P, 2 times 10 to the minus 3 meters. And you have these values showed. So you still have these two set of equations. So you can still find A's and B's, right, with those equations. So it's not as complex as trying to solve everything. But in this problem, we have a complication. The maximum pressure drop is 50 psi. And so first question is, what is the upper limit of the flow rate? So that's almost exactly the same problem as before. But then when the catalyst was spent, a similar batch is not available. And now we have to pack the bed with a second batch with a smaller diameter of 1 millimeter. And then what would be the maximum allowable rate if the pump is limited to 50 psi? Now, with a smaller diameter particle, you're typically going to have a decrease in flow rate, because the smaller diameter basically decreases your increases your pressure drop in the system. Okay. So we start with the same equation as before, meaning we're going to do this minus delta V equals AQ plus BQ squared. And we're going to solve it using these equations here, where I have, say, 9.6 equals 12. And I'm going to, let me back up a little bit and show you something so that we do it the right way from the beginning. So if I go back here to these equations, you see that I said that all of this is A. But in this problem, the diameter of the particle is not a constant anymore. So what we can do is that we set up a new equation in which we have a constant, but the diameter of the particle is out. So that I can take this and say, well, it's still A, it's just a constant, but I'm going to put here dP squared. And here I'm going to put B and dP. And so if I use that equation, then I can solve for any condition in this problem. So 9.6 psi equals A times 12 cubic feet per hour over 2 millimeters squared plus 144 feet⁶/hour squared divided by 2 millimeters, and I have to have a B there, kind of running out of space. Second equation is 24 psi equals A times 24 over 2 squared plus 576 over 2b. And I solve for A and B there. And A equals 2.38 and B equals 0.034. Note that I'm not putting units to A and B. They're very complex units, but you can find the units if you wanted to. You see that PSI, each of these terms should be in terms of PSI. So at the end, the A's and B's have units so that it cancels out the feet cubed per hour and millimeters, and then and have a PSI there. So then I have an equation that looks like this, minus dP equals over dt. Okay. And obviously this only works if the flow rate is in cubic feet per hour, the diameter of the particle is in millimeters, and the delta P is in PSI. Those are the numbers that we have. And so with 50 PSI in a 2 millimeter particle, we're going to have this equation. And with 1 millimeter, we're going to have the same equation, but with 1 here, right? 1 squared and over 1. And so we're going to solve both of these equations with a quadratic formula, so that we have here this Q equals 39 in minutes to get this number, 39.5 cubic feet per hour, and this one is 16.9. So yeah, notice that it is a big change. You see the difference between the two. The division by 2 and 4 makes this flow rate less than half. Okay. Now the second part that we wanted to cover is filtration. And filtration comes in very different setups. In the setup that we are showing here right now is what we call a plate and frame filter. They're very common in the chemical industry. It is essentially a bunch of filters. So you can see this white filter right here. And it's basically sandwiched with a frame that holds it in place. Liquid will come through these tubes and then get into each one of these filters, and then eventually will leave through the other side. The advantage of these plate and frame filters is that they are easily reused. You can open, wash them, put them back together, and do another batch. Obviously, the disadvantage is that you have to, it is sort of a batch process. But that is true for most filtration systems. You have to either change the filter over time, or clean it and put it back. In some cases in the chemical industry, that filter is collecting something that is the product itself. For you can imagine something that precipitated in a, say, in a pharmaceutical industry, something that precipitates that is your active ingredient. And now you need to recollect it from the filter in order to use it. In some cases, this is the case in this example, you're basically trying to remove solids from a liquid that you have, and then that solid will be discarded. The solids that form are called the cake. So you have now here a filter with a fairly thick cake on it. And what I'm typically that filter is very porous. So it has a very small frictional loss along the filter itself. But the problem is the cake, because the cake will deposit very small particles. And when you deposit small particles over time, they get thicker and thicker, right? And so you see that that looks pretty much like a packed bed, but a packed bed that gets increasing over time. At some point, this cake will be so thick that you can no longer pass liquid through, or the liquid flow is very small. And at that point, it's time to change your filter or clean your filter. In the example that I'm showing, by the way, is an example of wine filtering. That's why it's that color of wine. So what you see there are yeast cells that were grown during fermentation, and now you don't want them in the final product, so you're going to filter the wine. And we're showing a wine filtration because most industrial chemical industry systems will not show, obviously, their equipment being used. Now, how is it that we are going to develop this equation for a filtration system? First, we're going to assume that the flow through the filter is laminar. And so we can use Darcy's law. We have U0, which is equal to Q over A. It's going to be equal to minus kappa delta P over mu L. Remember the definition of kappa a few slides ago. And then we're going to have to, and notice that I put here Q in differential form. It's the change in volume over time. And that's going to be useful because we're changing things over time in the filtration system. The second thing that we need to determine here is the value of L, because L is the thickness of the packed bed, but the packed bed is now the cake itself. So you see that the resistance of the filter itself is neglected, so that we are only focusing on that cake that forms, and that cake is essentially the thickness of my packed bed according to Darcy's law, but that is changing over time. So we need to define the cake based on this equation. So in this equation, we are saying that we introduce a new term where alpha is the volume of the cake per volume of filtrate. And so what that means is and if you look at it from this perspective, is what is the percent of the volume that you're filtering that is solid. If your volume, essentially, if your filtrate, the fluid that you're filtering has very little solids, then that alpha is very small. And that value of L will increase very slowly. If your filtrate has a lot of solids, then you have a higher value of alpha, right? So we're going to say volume of filtrate over volume of cake, and then we multiply by volume of filtrate. So that gives me the volume of cake, and I divide by area. So volume of cake over area gives me the thickness of the cake. And then I have that second equation there, which essentially using this definition here to replace the value of L. And so with this equation, now we have two options. Well, two simple options. There are other options, but we're going to focus on these two simple options. One is that the pump that we use is a constant pressure, and another one is a constant flow. We didn't go over different pump systems, but I can give you a few examples of what constant pressure versus constant flow is in a pump. By the way, pump is one of the unit operations that we discuss in the full class of fluid mechanics. There are certain pumps that are called, say, a diaphragm pump. And that diaphragm pump works by a diaphragm that is moving, that basically has some sort of piston, and the piston is moving that diaphragm between a push and pull, push and pull. Those types of pumps pump at a constant flow. The diaphragm collects a certain amount of liquid and then pushes it. Another one that is a constant flow is a peristaltic pump. In a peristaltic pump, you have a tube, let me put it like this, that is being pushed by a pump that has some sort of rolls, and you're basically moving these rolls around and pushing the tube at a constant rate, and therefore you have a constant flow based on the diameter of that tube. Versus a pump that is that works based on pressure. At a constant pressure, for example, and similar to how we did the problems in packed beds, you have centrifugal pumps where you have basically one of these centrifuge systems. The fluid enters through the center and leaves on the side. You probably have seen some of these pumps are very common, and these typically work at a pressure relationship rather than a flow. And when the systems like these where filtration occurs are very low flow, then the correlation is that this pressure is more or less constant. So you can assume a constant pressure. Now, we take this equation and we say, where we're going to use this as a constant pressure, we're going to integrate this derivative of volume over time. To do that, I need to move that volume to the side. So I have VdV on the left-hand side. I have the pressure constant. Kappa is constant, area is constant, mu and alpha are all constants. So they go outside of the integral. And we're going to do that integration of VdV delta t, where at Time 0, my volume of filtrate is 0. And at time t, my volume is going to be, we're just going to call it V. So that this turns into V squared over 2, right? And this will turn into T. And when I solve for V, I'm going to have V equals the square root and of all of this times T, and you see the 2 here that we had in the integration went in there. So this equation is the equation for a constant pressure filtration. And then another option is that we have a constant flow rate. Now, when we have a constant flow rate, then dV dt is not changing. It's just Q. And so that's very easy. I can put Q squared. I'm also using this definition of volume equals Q over T so that I can take this volume and turn it into Q over T. I'm not looking to do. Turn it into Q over T there. So let me write it here. Oh, how did I come here so quick? 1 over area times Q would be equals to minus kappa area delta P over mu alpha, and I turn that volume into Q over T. Oh, sorry. It's not Q over T, it's Q times T. So the T goes at the bottom. And then I can solve for that delta pressure. And we say, well, at that constant pressure, at that constant flow rate, the pressure is going to be mu alpha Q squared T kappa over area. So this is constant flow rate. So I hope that you understand not only the equations, but the implications. If you run at a constant flow rate, the pressure will be low at the beginning, and then that cake will start accumulating until the pressure increases. At some point, the pressure will be so high that the pump will not work anymore. So even though it's a constant flow rate, you have to understand that there is a maximum pressure to your constant flow rate pump. You cannot just keep pumping and that cake increasing and increasing. Therefore, what's most important about a constant flow rate filtration is to track the pressure over time. Versus at a constant pressure, what will happen is that your flow rate will be very high at the beginning, and then the flow rate will keep decreasing because your cake keeps increasing. So then the volume over time becomes smaller and smaller, okay? So we'll do a problem here so you can get an idea of how to use these equations. So a company is filtering a powder from a water solvent mixture. We are given the viscosity and the density of the water solvent mixture. It contains 0.1% solid particles. So that means that alpha, which is the fraction, is 0.1 over 100. So it's 0.001. That means that for every liter of volume of that water solvent mixture, there is 1 milliliter of solid particles. The cake has a porosity of 0.2, And we're using a plate and frame filter that is 1.5 by 2. So that gives me the dimensions and the area that I can calculate. We have a pump that delivers a constant pressure of 30 kilopascals. And so the frame is only 1.5 centimeter. The frame used is a 1.5 centimeter wide. That basically is, imagine this is the filter. And so you have a frame with the liquid that is 1.5 centimeter wide. And so they can only operate this until the cake is 0.5 centimeter thick, which is a pretty thick cake nonetheless. So what would be the volume filtered and the time it takes to filter? Okay. Now to solve this problem, we're going to first collect a few parameters. We already said this is 0.001. We have the diameter of the particle as 10 micrometers, so 10 times 10 to the minus 6 meters. Epsilon is 0.2. The minus delta P is 30,000 pascals. The length of we have a value at the end that will be 0.5 centimeter. And then my area of the filter is 1.5 by 2, so 3 meters squared. Okay. I'm going to use the equation of constant pressure, which is this one. By the way, I was given mu as 0.9 centipoise. Sorry. And so you see that in this equation, I do have most of the things that I need. I'm trying to solve for the time, but I also don't have the volume. So it's kind of a weird start because I do not have two of the things that I need, the volume and the time. But I don't have kappa yet. So let's calculate kappa because that's an easy one. I have dp squared epsilon cubed 150 times 1 minus epsilon squared. And so this is an easy calculation. 10 times 10 to the minus 6 meters, 0.2 cubed over 150, 1 minus 0.2. You'll see that this is a very small number. Values of kappa are typically in the 10 to the minus 10 to 10 to the minus 15 for this type of system. Now, the reason why there are two unknowns is because we have another equation. And the equation is the thickness of my cake. The thickness of the cake is already given. And at that thickness, I can calculate my volume, right? The volume, just by mass balance, is determined on the fraction of solids that determines 0.5 centimeter of cake. So to make 0.5 centimeter of cake, I need this volume LA over alpha. So I have to change this 0.5 centimeter to meter. I have 3 meters squared and 0.001. So that gives me 15 cubic meters. So now that I have that volume, then I can solve for time. Time equals v squared mu alpha over 2 minus delta p kappa a squared. Okay. One thing that we need to do, and I'm going to do it here, is to change the units of centipoise to standard units, which is kilograms per meter second. So 1 centipoise is 0.001 kilograms per meter second. So now I have everything I need. 15 cubic meters squared, 0.0009 kilograms per meter second, 0.001 divided over 2 times 30,000 kilograms per meter second squared, 8 times 8.3 times 10 to the minus 15 meters squared, and 3 meters squared. If you follow the units, you should have just seconds in there. All the others cancel out. That gives you 45,000 seconds, which is about 12.5 hours, if I remember correctly. Yes, 12.5 hours. Okay, so that basically ends this class and the part of microfluid mechanics. And you will now have a new class on microfluid mechanics to look at. Okay, thank you.